Hi, my name is Angela Dawn, and I'll be presenting the paper Characterizing Cyber-Physical Attacks on Water Distribution Systems. So first, a couple of acknowledgments. The author Sridhar Adappu et al. This paper was presented in the International Conference of Applied Cryptography and Network Security in Rome, Italy, October 19 to 22nd, 2020. I've also provided links to this paper in the following link. So a little bit of background, water distribution is a critical resource. So these systems use cyber-physical systems controlled by industrial control systems to process inputs and make decisions that initiate actions on the physical process. For this reason, attacks on critical infrastructures like water distribution centers can be catastrophic. There has been a rise of successful cyber attacks on industrial control systems. In 2016, Kimuri Water Company was victim to an attack that exposed private information of over 2.5 million customers. This illustrates a need to evaluate the security of existing critical infrastructures and develop effective protection methods to guard and understand attacks on systems. For this purpose, this paper presents an experimentation on WADI where researchers try to answer the following questions. The first one being, how do cyber attacks impact a water distribution system? And the second question is, how does knowing the response of a CPS to one or more cyber attacks help in designing an attack detection mechanism? So this paper aims to find the answer to these questions through design of 6 attacks on a water distribution testbed. But first, some preliminaries. Industrial control systems are found in plants such as water treatment and distribution. It is important to note that the more complex the ICS, the broader the attack surface for both cyber and physical parts of the plant. The software on the ICS is also vulnerable to attacks due to legacy code, missing security patches, and/or lack of resources available to maintain the software to secure standard and guidelines. ICS consists of distributed supervisory control systems. This means a variable number of POCs talking to each other via sensors and actuators on a local network via different layers, also known as a field bus network. The increased use of information technology on control systems has opened a risk for critical information about these control systems. This information includes, but is not limited to, temperatures, level indicators, sensor signals, and other information. So next is WADI. This study uses WADI, a water distribution testbed that presents a scaled-down version of a large water distribution network in a city. This testbed consists of 3 stages. The first is the primary grid. This grid contains 2 raw water tanks that are fed by 3 incoming sources that are the public utility board, the return water grid, and a water treatment plant. The primary grid monitors the levels using a level sensor. Analyzers in this grid measure pH, turbidity, conductivity, and residual chlorine. The second stage of the testbed is a secondary grid. The secondary grid contains 2 elevated reservoir tanks, consumer tanks, and contamination sampling stations. The third stage is a return water grid. The return water grid contains water quality analyzers that check water quality before pumping it to the primary water grid. Communications. Each stage of the testbed is controlled by 3 PLCs. These PLCs use compact RIO, Schneider Electric remote terminal units, and SCADA pack to measure water quality. There is a total of 103 sensors and actuators measuring water levels, water quality, flow rates, pressure, and status of motorized values and pumps. WADI has 3 levels of networks. Level 0 is a communication between POCs and sensors over Modbus RS-485. Level 1 is the communications over National Instruments publish subscribe protocol. And Level 2 is the communication between HMI and plant control network. This interconnection of HMI and Level 2 with workstations and POCs allows remote monitoring. Identifying vulnerabilities. Eternal Blue, an exploit on Microsoft Windows used for the WannaCry ransomware attack in 2017. It is a vulnerability in the SMP, or Server Message Block Protocol. This exploit mishandles the packets from remote attackers that leads to access to the system. This attack has been studied and identified as an emerging threat to critical infrastructure. Default admin password on web server. This vulnerability exists because manufacturers follow default passwords. If the operating management do not change the default password, an attacker can use the default password from each manufacturing unit and exploit the system. RESTful web service. LabVIEW allows VIs to be equipped with RESTful web services, which manipulates the data via HTTP methods like GET, POST, and etc. These services don't require any authentication by default. Modbus Serial and TCP. P2A and P2B run Modbus TCP, while analyzers installed in P1 and P3 are connected via Modbus Serial. This protocol was not designed for security as it prioritized safety. For example, if you can own a device running Modbus, you can ping it. There are libraries in Python capable of speaking Modbus and specifically PyModbus. This library can be used as an attack tool to read and manipulate data on 8 sensors connected in P2A and P2B related to water quality. Objective-C program that speaks NISP. C# and Visual Basic libraries speaking NISP were found. These libraries allow attackers to write and read basic data from sensors and actuators in the plant. Custom VI that interacts with a Python script. A Python package was written to construct more complex attacks using special virtual instruments or LabVIEW programs that read and write to the cluster variables. This is critical because the NISP implementation in the water distribution system plant has no authentication or access control. If an adversary can access a network, they can control an entire plant. The importance of addressing these vulnerabilities is to highlight the fact that the network is very open, has no authentication in place, and relies on different nodes. Attacks Introduction. This study assumes the attacker can enter the system through vulnerabilities and social engineering. It also assumes an attacker has the process, communication knowledge, and access to the communication channels. Intentions. In this study, the intents of the attack were 1. To stop water supply to the consumers. 2. Damage water pumps in water distribution systems. 3. Overflow the water tanks. 4. Wastage of water by leaking the pipe. 5. Burst the water pipes. And 6. Manipulate dosing mechanisms in a water distribution system. These intents are taken from existing realistic attacks and incidents on water distribution systems. Attacks were divided into 2 categories. 1. A single point attack where only one sensor or actuator is attacked. And 2. A multi-point attack where the attack occurs on more than one sensor or actuator. So first we'll discuss the design of the single point attacks for this study. For attack 1, this is an attack on level indicator 1LT001. It is a level indicator that measures the level in the raw water tank in stage 1. The intent of this attack is to block the flow of water to the elevating reservoir tank. The attacker sets the simulation variable to true. This variable is located in the shared variable cluster of 1LT001 level indicator. The attacker also sets the simulation PV to 40 while setting s-empty to 40 using a script written with NI-exploit library. Attack 2 is an attack on the 2LT002 level indicator. This level indicator measures ER tank 2 level in process 2. The purpose of this attack is to stop flow of water to consumers and damage the pump. In this attack, the attacker sets PV to 80 by running a continuous loop. This causes the state of valves and pumps to remain unchanged, but the level of water falls in both the raw water tank and the elevated reservoir tank. Attack 3. This is an attack on motorized valve 1MV002. This valve is an actuator in process 1. It contains the current status of the respective motorized valve governing the flow of water to the drain. The attacker sets auto to false and forces open the drain valve. This causes the motorized valve to stop working according to the original program logic. The intent of this attack is to stop the flow of water to the consumers. Attack 4. This attack is on motorized valve 1MV001. This motorized valve is an actuator in process 1. The related shared variable contains the current status of the motorized valve governing the inflow to water to raw water tanks. The attacker sets auto to false and sends the close command. The intent of this attack is to block flow of water to raw water tank. Next, we'll be discussing multi-point attacks. Attack 5. The attacker targets multi-stage, multi-point attack across the process P1 and P2. The intent of this attack is to supply contaminated water to the elevated tank. Attack 6. In this attack, the intention is to cause intermittent supply to consumer tank. It is a single-stage, multi-point attack where the two actuators targeted are 2 MCV 101 and 2 MCV 201. So results. Figure 4 shows the attack on 1LT001 in which the attacker alters the reading from 48 to 40 of the reserved return water tank level, which corresponds to a low state. In the low state, the controller sends the command to fill the tank. The low state also causes there to be no flow of water from the primary grid to the secondary grid, even though there is a continuous supply of water to the return water tank through the pub value. Attack 2. In this attack, the tank level is set to high state, which leads to no flow of water from the return water tank to the elevated reservoir tank. However, the ER tank continuously supplies water to the consumers. The ER tank will move to an empty state and the booster pump will continue to run since it reads the high state. This will cause damage to the pump if there is no physical protection. Consequently, supply to consumers stops completely. Attack 3. Drain valves 1MV002 and 1MV003 are forced open, causing water to start draining from the return water tank. When the water level in the return water tank reaches the low level state, the pub inlet valve turns on to fill the tank. The settings of these two valves, draining and filling, leads to water supply from the return water tank to the ER tank. This causes water supply to consumer tanks to stop when the elevated reservoir tank falls to 35% of the maximum tank level. Attack 4. In Attack 4, valve 1MV001 is forced shut, which leads to no water in the return water tank. From figure 13, we can see that the return water tank level is kept at 40% as a result. This results in no flow from the return water tank to the elevated reservoir tank. However, the elevated reservoir tank continuously supplies water to consumers until it reaches an empty state and the water stops flowing to consumers. Attack 5. In this attack, the attacker launched multi-point attacks on one AIT-001 and two MV-003. The attacker manipulates the valves at precise times to contaminate the water supply. As a result, water from raw water tank will be pumped to the elevated reservoir tank. Similarly, Attack 6 is launched to achieve the attacker's goals. So, now to answer the research question 1, how do cyber attacks impact a water distribution system? From the result of the 6 attacks, researchers state an attack may lead to any one or more of the following undesirable consequences, and these are tank overflow, pressure drop at the consumer end, no water at the consumer end, and equipment damage. In addition to these tested attacks, other impacts can be organic and inorganic contaminants added to the water and chemical sensors compromised to avoid detection. So the next research question was, how does knowing the response of a CPS to one or more cyber attacks help in designing an attack detection mechanism? Well, traditional attack detection is often based on network traffic monitoring. Proposed water marking schemes are based on control theory. It is well understood that cyber attacks or faults on the system affect specific sensor readings. Finding detection mechanisms that can detect attacks, like the ones performed in the study, are the future. So for the conclusion and future work, the outcome of the study highlights the importance of testbeds in understanding stealthy and a variety set of attacks and practical issues in operational water distribution plants. This study also demonstrates an attacker can likely achieve an attack when adequate resources are available and the accessibility exists. Future work illustrated in this paper includes understanding more stealthy attacks and the implementation of a prototype defense mechanism in WADI. Is related work. So, open research challenges. Researchers have presented challenges in safety and security against cyber attacks that need to be addressed while designing a CPS. Sajid et al. Explained the integration of IoT and SCADA systems with a focus on security and how to integrate and create intelligent ICS using the internet. Humayed et al. Surveyed literature on cyber-physical system security and presented an orthogonal framework consisting of security, components, and system perspectives. They focused mainly on 4 CPS systems such as ICS, smart grids, medical devices, and smart cars. The next one is attack modeling and analysis. Attacks have been modeled as a noise in sensor data. Attack models designed specifically for CPS include a variety of deception attacks, including surge, bias, and geometric. Such models have been used in experiments to understand the effectiveness of statistical techniques in detecting cyber attacks. Tajodia et al. Proposed a detailed procedure for modeling cyber systems using attack graphs. Such graphs model practical vulnerabilities in distributed network systems. Chen et al. Have proposed argument graphs as a means to capture the workflow in a CPS. The graphs are intended to assess a system in the presence of an attacker. The graphs are formed based on information in the workflow, such as use case or state, physical system topology, such as a network type, and an attacker model, such as an order to interrupt, power based on information in the workflow. Such as use case or state. Physical system topology, such as network type and an attacker model, such as in order to interrupt power supply, physical tampering, network connection, denial of service, and etc. Type graphs and Bayesian defense graphs are a few other important contributions to the modeling of cyber attacks. Attacks on water systems. Amin et al. Studied attacks on water canal systems and presented attack detection methods based on control hydrodynamic models. However, this paper focuses on an ICS system consisting of a few sensors and actuators. The formal approach is used to analyze the security of a water treatment system. This paper aims at investigating the impact of attacks on a large system such as WADI, which has more than 100 sensors and actuators. Ricardo et al. Presented a modeling framework to characterize cyber-physical attacks on water distribution systems. This framework consists of a few categories of attacks and IPANET simulation models. The analysis is applied to C-Town network to show the usage of the framework. This work is mostly performed in a simulation environment, while the study reported here was performed on an operational water distribution system. This research is helpful to understand the differences between simulation-based attack investigation in water distribution systems, real-time water distribution attacks. Attack detection in water systems. Mitchell and Chen surveyed intrusion detection techniques for CPS. They presented existing works based on classification tree. They also presented the advantages and limitations of the techniques. The use of invariants for detecting attacks on CPS has been proposed and evaluated by several researchers, such as in 30. In this work, it is claimed that the use of controlled invariant sets in detecting cyber-physical attacks uses little information about the controller and hence is useful for a large range of control laws.